Yes, we are ready to go now. Yes, please.
Okay, so Ming Sheng has asked me to say a little bit about how we arrived at and developed the band-by-band conjugate gradients methodology. So I'm going to kick off with that. So that really comes at the end of a 2-month stay that I had at Cornell University in 1988. So Mike Teeter, who was one of the people at Corning, also had a position at Cornell University, and he invited me to visit for 2 months over the summer. Worked on a number of things, but the final day he said, oh, we should go out for lunch. So he drove us down the hill in his sports car, and we went to a Chinese restaurant. I'm sure Doug Allen was there, maybe some other people as well. So we had a very enjoyable lunch in this Chinese restaurant, and then we drove back up the hill in his sports car, and we were just sort of talking in the office, and he said, there's a problem with this car parallelo method. It's just far too slow. And I think we all agreed with that it was actually, it was better than what had come before, but calculations took a very long time. So he said, I know how to solve it. So he sort of, picked up a piece of chalk, marked on a blackboard. And essentially he went through the ideas of conjugate gradients. And so he said, our problem is that we're not directly searching for the minimum. Conjugate gradients directly searches for the minimum, so this will be so much faster. What do you think? And he turned around with a great big sort of hurrah, and I just said, that'd be infinitely slower than what we're doing at the moment. And he was somewhat taken aback by that. And the reason I said that was that he was talking about just minimizing the Hamiltonian, not including self-consistency. And as we know from the thing that was called charge sloshing, which gets bigger and bigger and bigger as you go to larger and larger cells, is that the charge tends to move around, and then when you put the 1 upon g squared Hartree potential in there, then you realize that it's moved far too far and it just goes backwards and forwards. And when you just minimize the static Hamiltonian, then you're always going to be doing that and actually moving too far in this particular direction. So I said, it's not going to be any good unless you include self-consistency in there. Which of course is not very difficult to do. You just take a trial step and then you update the density in that direction, and then you know that you can then get the minimum not of the static Hamiltonian, but of the Kohn-Sham energy functional. Okay. Why did we go band by band rather than all band, which other people were doing, particularly Mike Gillen? Simply because of memory requirements. So really the driving force for me in the early days of developing what became CASTEP was to do bigger and bigger systems so you could do new science. And if you did all bands conjugate gradients, and of course you had to keep previous conjugate directions, and that meant you need multiple copies of the wave function, and so that was going to be much more memory intensive, which was really the rate limiting step with computers at that time, compared to doing it by band. So that's why we did that. Anyway, so we talked through his ideas. I came back to Cambridge. I worked with a postdoc here, trying to implement it. Mike Teeter tried to implement it back in Corning and Cornell. And it must have been sort of several months later, I got a phone call during the day from Mike Teeter. And it was, I've done it, it works. And it's like, okay, calm down. And he was saying that, yes, I've got the conjugate gradient scheme working, I've applied it to silicon, and it is incredibly quick, because of course it just goes blop, straight to the minimum really, really quickly. So I said, oh, that's great. And he said, there's a problem. Of course, being Corning, their main interest was on glasses, okay? So silica rather than silicon. And he said, when I run it on silica, then it takes much longer, okay? And in fact, this has been discussed a little bit back here with Richard Needs. It was Richard who pointed out that what you need to do with all these gradient methods is to precondition so that your gradient direction is not perverted by the Hamiltonian giving you a wrong direction, but preconditioning in, and you get a direction which is closer aligned to the true descent of the energy surface. So Richard had outlined that to me, so I just said to Mike, no, everyone knows how to do this, you just need to precondition. And he went, and I said, basically you just need something that's kind of like constant up to the point where you get sort of the bandwidth of the material, and then ultimately it has to decrease like one upon the kinetic energy to cancel the excessive weighting due to the kinetic energy in the Hamiltonian. And I could just see exactly what Mike Teeter did, because he absolutely loved the Maple program for symbolic manipulation. And I could just see he would have wandered over to his computer, he would have sat down, he would have called up Maple, and he would have said, right, I need a function that turns over at this point, and it has 0 first, second and third derivatives, you know, at 0 energy, and then goes flat, and then turns over and turns into 1 over kinetic energy. And that is the reason that you got that sort of, you know, fairly complex form for the preconditioning function in CASTEP, because he demanded so many derivatives to be 0 at 0 energy. I mean, you know, you could have done something with a lot less, but it's fine, you just tabulate it. Anyway, I think I was in bed, it was late at night the same day, I was back home, and the phone rang, and there's Mike Teeter going, it works. That basically the preconditioning had meant that silica was converging just as fast as silicon. And I said, that's wonderful, Mike, but it is kind of like 1 o'clock in the morning here in Cambridge. And, you know, that basically was the story of the development. It's interesting because, I say, you know, Mike Gillen was working on an all-bands conjugate gradient methods, as were other people. I think Carl Parinello with Ivan Stich also worked on a conjugate gradients method. So the really interesting thing, which again has never been completely analysed, is that an all-bands conjugate gradient scheme definitely converts the energy faster than a band-by-band scheme, but a band-by-band scheme converges the forces much faster than an all-band scheme. And as most of our calculation is getting forces which are represented enough to take us towards a minimum energy configuration, then clearly getting the forces accurate fast is much more important than getting the energy. Yeah, you know, eventually it will catch up. And as I say, I mean, I don't think there's been any analysis of why there was this enormous difference between the technologies, but band by band, yes, you know, there were more efficient ways of getting the energy, right? But actually, it was a very, very efficient way of getting the forces. Anyway, it kind of got implemented, and it kind of, you know, took off. And that's how we got to band by band. And so band by band was purely motivated by memory considerations, because that was our rate limiting step at that time, and didn't really begin to become overcome until you got to parallel computers with much larger memory available. Yeah. Okay. So that was number 1 on the list of things that you wanted me to discuss. The next one was the finite basis set corrections. Okay. So briefly, the introduction to that was something that was known very, very well back in the early days of density functional theory, plane wave superpotential calculations, which is that you didn't need to go to absolute convergence of the energy of a structure to be able to work out energy differences between it and maybe a frozen phonon deformed structure. So that energy difference converged a long time before the absolute energy did. Okay? And I'm sure it was Volcker who said this, or it was, you know, clear from it that you know, why is the energy still going down? Well, of course it's variational, it has to go down, but the only thing those very high energy plane waves can be doing is getting a better description of the core. That's driving the energy down, but of course the whole of the idea of the superpotential is that the cores don't really matter that much for so many of the physical properties. So both of the structures will be going down in energy at the same rate when you'd converge the energy difference, even though the absolute energy wasn't converged. Okay? So that was kind of like known. And then the other thing was that everyone observed that when you started changing the volume of a unit cell, because you had a finite energy cutoff and because you had a finite number of K points, then every now and again there'd be these sort of abrupt drops in the energy. Okay? And what they corresponded to was, of course, when you compress the cell, the plane wave energy is increased, we impose a fixed plane wave cutoff, and suddenly a whole set of plane waves would drop out of the basis set, As a result, the energy would go up because you didn't have so much variational freedom, you didn't have so many basis states, okay? So you put the two together and it's clear that if you're in that regime where you converge the energy differences, then all that's happening is your description of the core is changing, but it's not affecting any of the physics, all right? And then you think, well, what do I need to get away from this? Well, you need higher energy cutoff, you need basically a continuum of K points, all of which are expensive and unnecessarily, because you've already converted the energy difference with respect to K points, with respect to the plane waves. So in fact, what you're saying is that each of your plane waves that you're losing at that time is just changing a contribution to the core energy, all right? And if it really is an energy difference is converged, then there can't be any directionality dependence in it. It's just losing a plane wave basis at that plane wave basis state at that energy. So what you can work out is how many plane waves would I need to have with effectively an infinite K-point grid at that energy, okay? Because of course, having got a finite number of K-points, then I have an integer number, which can be very different from that. And if we believe that each plane wave at that energy contributes this amount of energy to the core, then you can just work out what's the correction needed to number of plane waves. If each of those plane waves represents a fixed amount of energy, then of course you can just fill in the gaps in between. And sure enough, this is what Graham Francis did. And what you find, I mean, I thought that it would probably mean that the steps weren't so extreme, so that things would be a lot smoother. But in fact, it got rid of the discontinuity completely. And that suddenly meant that you didn't have to worry about going to much higher energies, much higher K-point densities. Simply by making this correction, then you started getting unit cell parameters and things like that very, very reliably, because you could see this very smooth energy surface once you made that correction. Okay.
Right. Okay.
Right. Next topic.
Unlike the finite basis correction, which is already fully integrated and automatic in Material Studio Castet, or Castet official release of Castet version, there's one thing which remain to be separate, but not very often used. That is the real space representation of non-local pseudopotentials.
Okay. Yeah.
And would you please
okay,
mention
so
a bit
the
of
next
that?
story. Yeah. Okay, so I said earlier on that my motivation for developing Castet and introducing things like conjugate gradients and so on was to be able to do large systems. Okay. However, there is a problem when you look at the asymptotic scaling of the methodology. So of course it is cubic scaling, because if you did explicit matrix diagonalization, that's cubic scaling. Even if you do iterative diagonalization, then the orthogonalization step is cubic scaling. So those are things that you would struggle to get round. But there was one further problem that was also cubic scaling, and that's calculating forces from the non-local pseudopotential. It's also cubic scaling, and it has a much bigger prefactor than orthogonalization. So trying to make things more efficient, trying to think of going to big systems, going onto parallel systems, then the problem was the most expensive part of all the operations as you went to big systems was going to be the non-local pseudopotentials and the forces. Now, in the older density functional theory codes, the ones that were much more sort of based on matrix diagonalization, then the way they got around this problem was by computing the density matrix. But of course the density matrix has the same size as the Hamiltonian, so is big, and of course the whole point, or one of the advantages of going to iterative diagonalization techniques, is that you only have to keep sort of the diagonal kinetic energy past the Hamiltonian, and either the diagonal if it's a local potential, or localized bits if it's the non-local pseudopotential. So already we didn't want to store the whole of the Hamiltonian matrix, so you couldn't go a density matrix route. So you have this problem that there was going to be this rate limiting step on going to big systems, which was forces due to non-local pseudopotentials. But of course, by by definition, the non-local superpotential is localized in space. And the early formulations, because they're in reciprocal space, you're of course summing over all of the plane waves. That's why you got the cubic scaling. So in principle, this is a problem that you ought to be able to do in a finite number of operations not related to the size of the unit cell or the number of plane waves per atom, per component of the non-local superpotential, because it's a localized function. But of course, because of the discreteness of the Fourier transforms, you don't get any of the smoothing benefits when you just look at a single atom. And if you just tried doing it in real space, it clearly didn't work. So we needed this because we wanted to do big calculations. It wasn't going to work with the level of representation that you had with what you had with the potential on the grid, what you had with the wave functions on the grid. And Dominic Smith had been working with Richard Needs, doing some really wonderful stuff on band gap narrowing in silicon. So finite temperature effects and how the self-energies affect the band gap of silicon. So really quite remarkable work. Anyway, he was about to go and move to Rutgers to work with David Vanderbilt. He had a couple of weeks left, and he came to me and he said, "Oh, Mike, have you got anything that I can do in a couple of weeks before I leave?" And so I said, "Well, we've got this problem that what we really want to do is do, for very big systems, non-local superpotentials in real space, but the amount of information on the grid within that circle, of course, is insufficient because it's basically delocalized over the grid. So, can you think of a way of actually addressing that problem?" And essentially what he did was find a way of manipulating the non-local part of the pseudo-potential so that the majority of the weight associated with that, even on a Fourier transform grid, became localized within a finite radius around the atom. Okay? Remarkably, you can play this game mathematically because there are bits of the representation you have that don't explicitly contribute to the energy, so they can be manipulated to basically localize the weight. And he basically did this in about 2 or maybe it was 4 weeks before he left to go to Rutgers. And without that, then we would have struggled to do the Takanagi 7x7 reconstruction, because that was like 400 atoms, so massive, and the cubic scaling cost, if we hadn't moved over to real space superpotentials, would have really restricted what we did. Yeah. Okay. Right.
So
next topic.
Next topic is the functionality or the method which many Material Studio CASTEP user, new user or experienced, liked very much, with high sort of degree of satisfaction whenever they have encountered a system not easy to converge self-consistently. If they switch on, no matter that is a magnetic ion, which is highly degenerate state, or rare earth magnetism, and they switch on ensemble density functional theory method provided just a switching between density mixing and EDFT. Wow, just so beautifully converged.
Right.
So please tell us that functionality and the story behind its development.
So that functionality. So one of the problems with band-by-band conjugate gradients, as opposed to all bands, although there's still issues with those, is that if you try applying it to metals, you get a problem, because if your band crosses the Fermi surface, you don't have that information just when you're optimizing the one band, and so you can get discontinuities in the energy because of band occupancy. The sorts of problems you're talking about when you start involving spin become even worse. Yes? So it's all about how much can you put in the full self-consistency and the genuine gradient direction when you get these points of basically, level crossings, things like that, which of course you won't get from a gradient or any derivative at a particular point. Yeah. So that was always sort of problematic with conjugate gradients, and to give Georg Kresser his due, then of course the sort of mixing schemes, density mixing schemes that he developed dealt with a lot of those metallic problems. Okay. But even with those, as you say, when you go to very difficult problems, they often are associated with magnetism, then you do run into problems. It's difficult keeping account of all of that. So this really was the work of Nicola Madari, who had done a number of metals simulations and calculations looking at surfaces and running dynamics on that, but came to some problems where you had problems converging, no matter how many things you add on to try and control the conjugate resonance. And essentially, it was entirely his idea of the way of dealing with this was ensemble density functional theory. So, yes, it's a technique that, if you like, guarantees absolute convergence, albeit at a cost, which is if it's a much simpler system where you don't get these instabilities, then of course some of the much simpler, say, straightforward conjugate gradient schemes will work much better. But as you say, the wonderful thing about it is it's a wonderful gold standard that it's always going to work for you. So if the quick and dirty, if you like, is not working for you, then you've got the fail-safe of switching it on. And did you see that paper recently where I think it was Phil Hasnip and others were comparing convergence rates of different algorithms against absolute stability?
Oh, no.
Yeah, so that kind of quantifies this thing about which methods work, how fast they work, but then also where do they start failing and not converging. So Phil was definitely one of the authors of that paper. And in half an hour I'll probably remember who the others were, but offhand it doesn't immediately spring to mind. But it kind of formalizes everything that was observed during this process that eventually led to let's have something that is absolutely guaranteed always to work. Okay.
Right. Okay. Right. Then as a final question of this interview, would you please say something about perhaps next functionality that could be useful for future CASTEP users?
Okay, so there are a lot of functionalities that exist in other very similar codes, so plane wave pseudopotential codes that aren't in the CASTEP code. I mean, you were talking about transport earlier on. So, you could make the argument that, CASTEP should include all these other functionalities. But I think, the world now is very different from the world when CASTEP was first developed. Pretty well all of these codes are now extremely well packaged, very easy to use, and one thing that I completely note when I see younger researchers' CVs is that they have experience of many different codes and very happily move between these different codes. So I think it's just being realistic. We're not going to end up with one super code that has every functionality. Perhaps it would be better if we had a more easily accessible sort of paper perhaps on the particular strengths of particular codes and why you might choose to use one rather than another for certain things. Probably it's just too politically dangerous to do that, so probably it won't happen. So I think my own feeling is, if there's a functionality, it's another code, unless it's so mainstream that almost everyone wants to use it, then CASTEP does some things particularly well, but if there's a competing code that has a functionality, I don't think it's crucial that CASTEP necessarily brings that on board. The whole reason for the rewrite of CASTEP was to provide this very stable, well-structured piece of software so that if you had a bright idea or a new idea of what you wanted to do research on that required new algorithms implemented in the code, that you had a very straightforward method for doing it. So to me, it's what goes into CASTEP will be what excites the next generation of researchers and what functionality that they want to bring in. So I know that you've talked about, you're going to now subsequently talk to the CASTEP developers group, because it's entirely up to them to decide what science they want to do, and that will, for the most part, determine the functionality. But as I say, it's a very different world now compared to when CASTEP started, and so easy to swap between different codes. Of course, there are some issues about the pseudopotentials available and all the rest of it, but I think the best approach is not to try and put everything into a single code, but just say, okay, if you want that, it's here in this code.
Right.
Go and access it, do the calculation with that, and then come back to CASTEP or something else to do other things. To me, the bigger issues confronting our field are making ourselves useful and relevant to real world problems. Okay? So we know we can design materials with particular properties, okay? But, and I think I alluded to this in the previous talk, more often than not, when people try and make it, they can't make it. If they can make it, say it's an ultra material, they find it cracks or it falls apart in normal environment. So it's not very useful. If we're really going to be helpful and really take on this challenge of designing future materials for the challenges that we have globally, I think we need to move to the next level of complexity and help people with designing their fabrication routes or understanding what's going wrong. So I would say that just being prepared to do more complicated things, work alongside experimentalists. In all cases in our field, the most effective things have been where you use this methodology to interact with experiment and add value on either side. And when it comes to things like fabrication, understanding failure modes, then you're not going to do it in Theoryland on its own. You've got to do it using the mixture of the methodologies. So, I think I will be trying to urge the community in that direction. And of course, the way this is typically being done at the moment is not by directly applying CASTEP because of the very limited number of atoms, very limited timescales, but to generate data that you can then use for machine learning to generate the potentials for these systems, and then you can access longer timescales. I think there is a move, a bit of a shift to this technology providing the input data that you use as part of a whole process. Of course, if you want to do some completely new property that, there's no data for, there's very little experimental data about materials, then of course you need that functionality in the code, so that will maybe motivate someone to implement it in the code, and then of course that data can go into a database, and then you can think about machine learning on top. So, I think we're kind of universally there to do many different things. Sometimes it's directly, providing the experimental data, something like spectroscopy, where you do the computation, you get outputs that can be used to help the person doing the experiment decide how to run the experiment. So sometimes it will be direct, but I think increasingly it will be providing input and then moving up to the next hierarchy of methodologies to allow much bigger systems, much longer timescales. But final warning to everyone, the timescales we can do even when we go to machine learned potentials, the number of atoms we can do even when we go to machine learned potentials is trivial compared to a real material expected to last for 10 or 20 years. Right? We're not going to solve these materials problems directly. We have to get insight, go back. The early days, everything we were doing, it was, Vulcan turned the idea of a computer experiment where you say, oh, why is this doing that? And then you ask let's constrain an atom. And what's the system do then? And if the system doesn't do the same thing, you know that is the atom that is critical in the process. Because we could do so little in the early days, then you had to think about how to extract value.
Right.
And you see this in numerous fields, that suddenly you can do so many things. So, I'm doing this, I'm doing this, I'm doing this, right? But if you step back, you're not doing the real world. We're not doing the timescales, we're not doing the number of atoms, even if we delegate part of the task to machine learning potentials. So the only way we're really going to make progress in these things is getting back to the thought experiment, trying to learn and understand the systems, and then there's the opportunity that we might be able to propose ways of intervening with a failure mechanism. Yeah. So my own feeling is the enormous advances. It's great that we can do much longer timescales. Great that we do far more atoms. Of course, without the density functional theory, you wouldn't have the data to be able to do that. But we also need to get back to thinking much more carefully, doing controlled computer experiments as a way of accessing the data we need if we're really going to, generate materials. And we're never going to do it entirely on the computer. It's always going to be an interaction between practical and theoretical work.
Right. I just remember one last question I forgot to put in the memo. That is, it has been 30 years since the formal release of CASTEP code, and will you comment on and share your observation on the unique route, or unique success story of this code? Why, after all 30 years, why the world do not see more of this kind of CASTEP story emerge, and what will be advice for future generation or future younger people?
Okay, a nice little small modest question. Yeah,
right.
Okay. So I think I might have mentioned the very early days when we were looking for some sort of commercial partnership as a way of continuing to support the CASTEP code. And it's true that whenever you're looking at tech transfer commercialization, then you can have the greatest product in the world, but there's always some degree of fortune, luck, just happening to encounter the right people, or the right people being in place to see the longer term impact of what you're doing. So I think in our case, we did visit a whole bunch of different modelling companies, but without any doubt whatsoever, it was clearly Patrick Coulter who had the vision of this will be important for our company and where we're going, even if that isn't going to really reach fruition for 4 or 5 years. Okay, so without doubt, without Patrick, then it wouldn't have started even. Okay, and then of course the inspired step of getting Victor Millman to look after the product and do all this interfacing and look after the code development. Again, it's about the right people. Yes, it's not the number of people, it's about the right people. Yes, so those were the critical steps. As I'm sure I said, in the sort of, after the point that the product was licensed, and actually it started selling really quite remarkably quickly. By 1998 we were up to sales in excess of £1 million a year, actually, when I think the exchange rate was about 1.6. So very quickly had moved forward. The expansion of the market was very much down to Keith Glassfoot, who was the first sort of product manager who was, I think he was the quantum product manager, but he came in and was like, okay, I'm going to push CASTEP, right? So, just endless enthusiasm and, a great salesman and really disseminated the fact that this could be useful to you. Then, of course, we hit the problem that, everything had been sort of, thrown together during the 1990s, people working on different things. We got the separation between the sequential code and the parallel code, and we were getting to the point, like pretty well every piece of academic software gets to, which is that you get code bloat. Yes, everyone writes their own bit of code, even if, I think someone said that at the point when CASTEP was rewritten, then there were 21 different conjugate gradients routines. because everyone said, "Oh, I got my one. Oh, let's just write this." I mean, it's much easier just to write from scratch and develop flexibility. Yeah. So the natural tendency, particularly in academia, is quick and dirty because no one really cares. All that matters is you get it working, you get your calculation done, you get your publication, and then you move on, and then, yes, it's there, but it's completely, of course, useless. So it was clear that if something hadn't happened, CASTEP would have the original CASTEP probably would have lasted for another sort of 4 or 5 years. Yeah. And then it would have sort of gradually declined. There's a thing in marketing called milking the brand, which is where you stop investing, but you're still getting sales, and they gradually decline with time. So, and I think I've said this before, there was this younger group of people, and they wanted to do novel science, which required a total energy plane wave pseudopotential engine to then build the capability on top of. It was clear that old CASTEP couldn't do it. Phil Linden had been asked to put linear response into CASTEP, and it was just such a mess that it just never was going to happen. Which is why he was the one who really pushed to say, let's produce a clean code, let's do it properly this time, and then I'll be able to do it. Whereas if I try doing it with the existing code, it's never going to happen. Yeah. So Phil convened the first meeting of actually lots of users of CASTEP, and the basic question was, do we want a nice clean code? Well, of course, everyone said yes, and then it's right, well, who is prepared to contribute to it? And then, of course, there was a much quieter response. But fortunately, there were 6 people who said, yes, we are interested in doing this. I think 3 of them had had formal computer science training, and the others were very into software, but with proper professional software development standards. And they talked amongst themselves and agreed that yes, they wanted to do it. And I'm not sure if I said this before, there was a 6-month window when they could have said yes. Any earlier, and it was too early on for people who were PhD students. They couldn't have contemplated embarking on something like this. And at the end of the 6 months, then some of the postdocs would have actually got academic jobs and would be too burdened to take on that task. Fortunately, the agreement to go ahead was in the 6 months. Okay, and they did it properly. Okay, they wrote an entire spec of the code before writing a single line of code, and then did a walkthrough of that, and then delegated off the tasks of writing the code, all with sort of modern software techniques, which I don't really understand. I was never quite moved beyond Fortran 77. And remarkably, in 3 years, in their spare time, because they were all sort of, doing PhDs or doing postdocs, or some have gone on to academic positions, then they generated this new code, right? But of course, it's 3 years of standing still, all right? You get up with a code that actually only does what the old code did. There was a lot of problem, persuading molecular simulations that this should become the new CASTEP. And the main reason that they were cautious is that they didn't believe that 6 people, even working full time, could have done the job, right? And certainly not 6 people in their spare time. So it was like, well, we might have had greater engagement early on, but we didn't honestly believe it was going to work, okay? And it is an absolute triumph, and it's never really had the recognition it ought to have done. But it did work. Towards the end, when it was clear that there was going to be code, it did actually do what the old code did, but was really tidy. Then, after numerous almost divorces, we were like, almost the sort of the final signature on the, never talk to each other again. Fortunately, they talked to each other, and it was agreed that this would become the CASTEP's code as distributed by Molecular Simulations. I don't think it had become Axeris by then. Maybe it had. I don't know. But you can see how rapidly things changed after that within an incredibly short period of time. Then the crystal nuclear magnetic resonance capability had gone in. And again, so work had been done on that. That was... I'm so bad at remembering names, but the person who did NMR originally.
Chris.
Who was he working with though?
Francesco Mari.
Yeah. So Francesco Mari had done
Yes.
NMR,
Right.
all right. And I mean, so this is great. This is such a typical story. Okay, so Francesco did, implemented an NMR capability, and it was absolutely brilliant. And it only worked for hydrogen. Okay, I heard about it from probably Sandro De Vito because he was close friends with Francesco Mari. And when I heard that, I said, "Oh yeah, well that's obvious, isn't it?" And it obviously comes down to the pseudo potential. Yeah. And I also said to Sandro, the person who will be able to sort this out is Chris Pickard. So, you need Chris to go and visit Francesco. There was so much resistance to Chris going to visit Francesco. So much resistance. But I kept pushing it, and eventually it was accepted. Of course, the outcome was the GPOR potentials. Suddenly you could do every element of NMR. Okay, so that had been done. Jonathan Yates here had, added that functionality, I guess, to the code that Francesco had implemented it in. But bringing all that into CASTEP took an incredibly short period of time because you had this modular code with most of the capability already there, and you just plugged it in. And so very quickly you had a fully working NMR code. So this having a code that is allowing you to do your own fundamental research. I think I talked about technology readiness levels last time. So, so that's TRL1 because you're doing something you don't even know it works. But also identical code being shipped to the commercial customers. This is how academic software should be. Right? I can assure you I have spoken to thousands of academics. They all agree this is how it should be done. And of course, no one does it. Because for most of our codes around physics and chemistry and engineering, all of it, it would mean starting again from scratch to write a properly configured piece of code, and that's 2 or 3 years where nothing is happening. Right? And of course, we're all so busy, we're all under vast pressure to get stuff out, that although everyone agrees it's the right thing to do, it never happens. We had an initiative in the UK called Software for the Future, which was meant to be funding to help do this, but of course the funding was completely insufficient to do the job properly. So it certainly did help by tidying up some codes, but it wasn't the start from scratch, do it properly, and then you have something that is both in a fit state to be given to commercial customers, but also is your tool for doing innovative things. So, the lesson has been there, everyone agrees it's the right thing to do, and of course no one actually does it. Yeah.
Wow,
that's life.
It's such a good analysis, observation, and also the experience you share to our audience.
Okay.
But thank you very much for this wonderful lectures. Or you
well, I think ramblings will be a far better description of what we've done.
Thank you very much, Professor Payne.
And I think it would be particularly interesting to get the views of the CASTEP developers.
Yes.
Because obviously they will have different views of this, but an interesting story.
Okay, thanks again.
All right, wonderful.
Yes. Okay.
Okay, so I will see you on Sunday.